Welcome to Brain Vision.
In this question, we are looking at the hydrogen atom. We want to find what is the photon needed to excite a hydrogen atom at the ground state such that it will emit the alpha line in the Balmer series. So the Balmer series, basically we are looking at transitions involving any excited state above 2 all the way down to 2. So say for example 3 to 2, 4 to 2, 5 to 2, so on and so forth, right? As long as the ending state is in the n equals to 2 state. So this is the Balmer series. So when we're looking at the alpha line of the Balmer series, we are basically looking at the first possible transition, right, with the smallest energy. This is the case when we have the transition from 3 to 2, right? N equals 3 to n equals 2. That means that our hydrogen atom, which is starting at the ground state, must be first excited up to at least the second excited state, which is the n equals 3 state, before it is allowed to undergo this 3 to 2 transition. Therefore, the smallest amount of energy required to give to the hydrogen atom would be E3 minus E1. Now we know that the energy levels of the hydrogen atom can be found by this general equation, 13.6 eV divided by n squared. So this will be just 13.6 eV 1 minus 1 over 3 squared. And this will give us 12.1 eV. So this is the minimum energy and minimum energy that must be given to this hydrogen atom to excite it to n equals to 3. Now the next part, we want to find how many different possibilities of emissions there are when you have this atom at the n equals 3 state. So now it's in the n equals 3. What are the possible photons that can emit before reaching to the ground level? So one possible would be from 3 to 2. Another possible would be from 3 all the way down to 1. And of course, there's an intermediate step from 2 to 1. So there's 3 different possibilities that could occur. So let us find the different wavelengths. So what we need to find the wavelength, we will need to find first the energy of the photon. So let us consider the first one, which is from 3 to 1 directly. Energy of the photon we already calculated is 12.1 eV. Wavelength would be just taking hc divided by the energy of the photon, where hc is 1240 eV dot nanometer. So we should get 103 nanometers. This is the first possible transition. The second one we're looking at is from 3 to 2. Right, in this case, the energy of the photon is just E3 minus E2. This gives us 1.89 eV. Therefore, we can find the wavelength. Which should give us 657 nanometers. Finally, the transition from 2 to 1. Energy of the photon be E2 minus E1. which leaves us with 10.2 eV. Therefore, the wavelength of this photon that is emitted, take hc divided by the energy, and we should get 122 nanometers.